Inference for proportions, the one-sample z-test and confidence interval, and the chi-square test of independence. The one-sample z-test and confidence interval. We use the one-sample z to test or estimate a single population proportion p. This can be a one- or two-tailed test, and it is a z-test just like our one-sample z-test for the population mean mu. Only here our population parameter of interest is p, the population proportion. So our data are always categorical. P hat, the sample proportion, is calculated as x over n and is our primary sample statistic. A test value for p must be supplied for testing. For example, test to see if the population proportion of women is different than 50%. We could also estimate p at 95% confidence. Using the Unit 4 Case Excel tool, we're going to test variable for gender using a test value of 0.5. So here, our one sample z-test requires us to input a variable number, here 4, and to specify a success category. This is going to determine what I'm testing because it's going to determine my p hat. So the success category, F, will determine X, 43 women out of N, 77 cardholders, so we get a p hat value of 0.56. Using a test value for p of 0.5, we could run the one sample z. Here we can see that z equals 1.0256, and the two-tailed p-value that z produces is over 30%. So quite clearly, here we would fail to reject the null hypothesis, which allows us to conclude that the proportion of women in the population is still probably close to 50%. We could estimate at 95% confidence what that true population proportion of women is. I'm 95% confident that the proportion of women is somewhere from approximately 45% up to about 67%. And again, 50% is clearly within the interval range. So stating our results formally for this particular one sample z-test, we would state that we do not reject the null hypothesis that p equals 0.5. In other words, we cannot reject the hypothesis that the population of cardholders is about 50% women. Now we can conclude further, because proportion is binomial, we could say that the distribution of gender is approximately 50-50. We only tested for the women, but because proportion is binomial, we can get the same conclusion for not women, or the complementary event. The chi-square test of independence. We use the chi-square test of independence to test whether an independent variable has a statistically significant effect on a dependent variable. For the chi-square test, both the IV and DV have to be in categories. Quantitative data can be used, but those quantitative data are recoded categorically to suit our chi-square test. The chi-square test assumes no association between variables. In other words, we're assuming as a null hypothesis no effect of the IV on the dV. Chi-square testing determines the significance of effect in general. However, it's the post hoc analysis that determines or shows specific effects. Let's look at an example of a chi-square test using our Unit 4 case data. This is the Excel tool that has all of our quantitative independent variables recoded categorically. And of course, we still have gender and education level, which are already in categories. Our dependent variable is the amount charged. However, here we can't use the quantitative data, variable 3. Instead, our dependent variable for chi-square testing will be variable 7, a recoded version of the amount charged. So the chi-square test can be used to test the effects of some independent variable on a dependent variable, and both IV and dV will be in categories. For example, let's test whether gender has a statistically significant effect on the amount charged. Both variable 4, which has two categories, F and M, and variable 7, which are in thousands of dollars. So there's 5 categories. 1, 2, 3, 4, and 5 are the category labels. So both IV and dV are in categories. So my cross tabulation shows the observed counts or frequencies for our n equals 77 cardholders. The chi-square statistic here of 19.17 is very strong and produces a p-value of only 0.0007, which is highly significant. The clustered bar graph shows the specific effects. So the p-value shows us a general effect, but it's some post hoc analysis that will show us the specific effects. The specific effects that we are looking at are proportion changes. So what is the difference in the proportions of men and women who spend in category 5? And we can see that the difference is notable. Here in category 4, there is a difference, but it's not nearly as great proportionally. Categories 3 and 2 also show notable differences. It's these proportion or percentage differences, the specific effects, that are pooling to create our strong chi-square result. So stating our results formally for this chi-square test of independence, we could say that we strongly reject the null hypothesis of no association between these two variables. Gender does, we could conclude, have a significant effect on spending category. Our evidence for making this statement, chi-square for 4 degrees of freedom, is a very strong 19.17 with a highly significant p-value. But it's our post hoc analysis using the conditional distribution table by independent variable or a clustered bar graph which will help us determine specific effects. The interpretation of our post hoc is critical. We're looking for notable differences in percentage of DV category between the IV categories. For example, here we saw that over 25% of the women spent in category 5, while just over 5% of the men spent in that same category. This concludes the program Inference for Proportions.